So in this video, I'm going to start out with a fairly famous mathematical problem called the Mutilated Chessboard. But since a fair amount of people are probably already familiar with that problem, I'm going to quickly transition into some related problems before leaving with a couple of challenge questions that I find pretty fun. Anyways, without further ado, the idea behind the Mutilated Chessboard is we're going to start out with, well, a chessboard, and we're going to try to cover it with dominoes. Each domino covers two adjacent squares on the chessboard, and our goal is to cover all the squares without having any overlapping or spilling over the sides or whatever. And you might be like, wait, that's super easy. Just lay them all side by side. So it kind of looks like this. And yeah, that would be super easy, but we've neglected to include the mutilated part of the mutilated chessboard. The chessboard we're supposed to cover with dominoes has two opposite corners removed. Can you do it? And if not, can you prove that it's impossible? If you haven't already heard this one, it's definitely worth pausing and messing with it for a little while. It's pretty satisfying once you see the solution. A hint, which I guess I could have my dog tell you if I was still doing that, is to think about the colors of the squares in the chessboard. It's an 8x8 chessboard, so we start out with 64 squares, half of them red and half of them gold. However, when we remove two opposite corners, we're removing two squares of the same color, red in this instance. So our mutilated chessboard has 32 gold squares and only 30 red squares. Now think about placing a domino. Each domino is going to cover exactly one red square and one gold square, so it's impossible to cover 30 red squares and 32 gold squares with our dominoes. The mutilated chessboard puzzle is impossible to complete. In the language of the previous videos, the number of red squares left to cover minus the number of gold squares left to cover is an invariant of the operation of placing a domino. Anyways, often the mutilated chessboard story ends right here. But for us, it's just getting started. You might wonder, in which ways can we mutilate the chessboard and still cover it with 2x1 dominoes? I mean, we know that if we're removing two squares, it's necessary that one of them be red and one be gold. But is that sufficient? It turns out that yes, it is. If you're removing two squares, as long as one is red and one is gold, there will always be a way to cover the resulting mutilated chessboard with 2x1 dominoes. This result is famous enough to have a name. It's called Gomory's theorem. The proof of the theorem is based around the existence of a closed path around the non-mutilated chessboard. What I'm saying is pretend that you are a chess piece and you're allowed to move up, down, left, or right one square at a time. You can start wherever you want, and what your task is to visit all 64 squares of the chessboard, each exactly once, returning to the square at which you started. Can you do it? Again, it might be worth pausing and trying to do it on your own before you see my solution. There's lots of different solutions, some taking advantage of various forms of symmetry. There's a cool spiral one, but the one that came to mind for me was to start in the upper left-hand corner, traverse across the top of the board, and then take advantage of some left-right symmetry, working from both the start and the end of the path until I can get them to connect. Now that we have our closed path, we can proceed in proving Gomory's theorem that no matter which two of the squares of the chessboard we remove, as long as one is red and one is gold, we'll be able to tile the resulting chessboard with dominoes. Let's start by removing the red square. For the sake of the animation, I'll pick one arbitrarily, but convince yourself that the argument holds no matter which red square is chosen. We'll think of this removed square as our new starting spot, and we'll number the squares according to the order that they would be visited if we followed our original path, but started here. We now need to remove one of the gold squares, and the important thing to notice here is that all of the gold squares are numbered with an odd number, so no matter which one I remove, our original path will be broken up into two different paths, each with an even numbered length. In case it's not obvious that the length of each of the paths is an even number, one way you can prove it to yourself is by noticing that the first path is numbered from 1 to 1 less than the number on the yellow square that we removed. However, all the yellow squares were numbered with an odd number, so 1 less than that must be even. So the length of that path must be even. And since we start out with 64 squares and remove 2, we have 62 squares left. 62 minus the even number of squares used in the first path leaves us with the even number of squares used in the second path, because an even number minus an even number is an even number. Anyways, if you're convinced that we have two paths of even number length, tiling the mutilated chessboard becomes easy. Just place them on the path. First domino covers 1 and 2, the next one 3 and 4, the next one 5 and 6, and so on. As long as we remove one red square and one gold square, all of our paths will have even length, so we can tile them, and therefore the entire mutilated square, with our dominoes. Okay, but what if we weren't using dominoes? What if we were using L-Triominoes, 1x3 dominoes, whatever you want to call them? Well, 62 is not divisible by 3, so we definitely wouldn't want to mutilate the chessboard by removing two squares. However, 63 is divisible by 3, so maybe we mutilate the chessboard by just removing one square. That begs the question, which square, if any, could we remove and still be able to tile the resulting mutilated chessboard with L-Triominoes? Well, since all of the work we've done so far has been dependent on the color of the squares, you might first try to do some analysis on red and gold squares. However, I think what you'll see is that because our tiles cover 3 squares at a time, it makes more sense to color the chessboard with 3 different colors, like this. When you're done admiring the beautiful animation, which I spent way too much time on, you might think to count up how many of each type of color square we have. Don't bother, I'll do it for you. There's 21 green squares, 21 blue squares, and 22 purple squares. Aha! Since each triomino, whether we lay it horizontally or vertically, is going to cover 1 square of each color, we have to remove a purple square. Just like that, we've ruled out 42 of the 64 possibilities for the square that we're going to remove. To help us keep track, I'll outline the only possibilities for removal in red. So could we remove any of these squares? Turns out no. And you can prove that fact with a clever 3-color recoloring of this chessboard. Look what happens when I rotate the coloring 90 degrees. There's again 21 green squares, 21 blue squares, and 22 purple squares. So if I'm going to tile the mutilated chessboard, I better remove a purple square so that I have the same amount of each. What I'm saying is that any square that's colored in green or blue can't possibly be removed. So previously, I narrowed it down to the 22 squares outlined in red, but 18 of those 22 are now colored in either green or blue, so there's only 4 candidates for the square that I remove. What I'm saying is by this coloring argument, for 60 of the 64 squares, if we remove that square, there's no possible way to tile the resulting mutilated chessboard with Triominoes. What about the 4 cells that we haven't yet ruled out? Just because we haven't yet ruled them out doesn't necessarily mean that we could remove one and tile the resulting chessboard with our Triominoes, but with only 4 possibilities, we can check them one by one. For the first one, there's probably some clever way you can place the Triominoes to guarantee you can cover the mutilated chessboard, but I just kind of started throwing them down until I found something that worked. And then rather than recreate the wheel, for the other 3, I just took my first configuration and rotated it. So we've eliminated 60 of the 64 squares as possibilities for removal, and for the remaining 4, we've explicitly shown a covering. We're done with this problem. Is there anything else we can do with these Triominoes? Maybe not with these Triominoes, but what about these Triominoes? Can you show that no matter what square you remove, you'll always be able to cover the resulting mutilated chessboard with these L-shaped Triominoes? A hint to doing so is noticing that we can take 4 of these L-shaped Triominoes and create a super L by arranging them like this. Why is that useful? Well, let's go back to our chessboard and think about what we'd be left with when we remove a square. Again, for the sake of the animation, I'll pick one arbitrarily, but convince yourself that this argument will hold no matter which square we remove. The key is to think about our 8x8 chessboard as being made up of 16 medium-sized squares. The removed square is going to lie in one of these 16 medium-sized squares, and we can always cover the rest of this medium-sized square with one of our L-shaped Triominoes. We now have one covered medium-sized square. That medium-sized square will always lie in one of these 4 large squares. We can fill out the rest of the large square with one of our super L's. And in the same way that we can make a supersized L from our regular L's, we can make a super duper L from 4 of our super L's. And that super duper L will fill up the remaining 3 of the 4 large squares, finishing our tiling of the chessboard. There's probably more we can do here, but I like to keep these videos around 10 minutes when I can, so I'm going to call that good and leave you with a whole host of challenge questions. We've seen dominoes in Triominoes, but what about Tetrominoes? Dominoes made up of 4 pieces that you may be familiar with from the game Tetris. I'm gonna call these pieces straights, steps, swooshes, snakes, and squares, because I like alliteration and that's what they remind me of. If we start with an unmutilated chessboard, it's really easy to tile it with straights and squares, and not much harder to tile it with swooshes. However, sometimes, like in the example in front of you, the edges of the pieces will form a straight line from one edge of the chessboard to the other. We refer to such a line as a fault line. The first of your challenges is to come up with a tiling of the unmutilated chessboard with swooshes that does not contain a fault line. Your next challenge is similar. Again, we're tiling the unmutilated chessboard and doing so in such a way that we do not create a fault line. However, this time we're using steps. For the remaining challenges, we're going to mutilate the chessboard by removing 4 squares of the chessboard in the shape of a square tetromino. So these 4, for example, or these 4. We're no longer concerned with fault lines. Your third challenge is just to show that you could not possibly tile this mutilated chessboard with straights. For challenge 4, come up with an argument showing that you could not possibly tile this mutilated chessboard with swooshes. And finally, for challenge 5, show that you could not possibly tile this mutilated chessboard with steps. As always, any thoughts, questions, or solutions can we put straight into the comments.